back. This is lecture 1 of 2 in section 4 of the course. In the last lecture we discussed mass transfer. How do you get sort of molecules of different types to interact with each other, move around throughout each other, looking at either molecular diffusion or bulk convection based diffusion. In this lecture I'll be discussing reaction engineering or chemical reactions, so looking at reaction rates and how quickly things are going to proceed, and that will relate to the size of reactor required to allow for that reaction to go. So I'll just open up my slideshow. So here we go. Now last week, or when we were talking about mass transfer, that's what allows the molecules to actually come in contact with each other. But that's not the whole story. For a chemical reaction to proceed, the molecules first have to come in contact with each other, but then they actually have to proceed with the reaction. And that reaction is somewhat dependent on sort of a few parameters. Like once they come in contact, how long is that going to take them? Well, it's related to the study of reaction kinetics. So anytime you're looking at how fast a reaction occurs, that's a reaction kinetics question. So this will probably be something that it might be somewhat familiar from chemistry, but it bears repeating here. So for a simple reaction, A plus B goes to C plus D, the rate of collision, so the actual molecules hitting each other, is going to depend on the temperature. The more energetic those particles are, the faster they'll be moving, the more random motion there'll be within the system, and therefore the more likely that collisions will happen. So the reaction rate is temperature dependent. However, not all collisions are going to result in a reaction occurring. It depends on things like the orientation of the molecules. If they're lined up right, they need to be lined up so that the reactive sites are going to interact with each other. Otherwise, if they're not quite lined up right, the reaction won't proceed. And they also have to hit each other with a sufficient energy, or then you have to hit each other with enough force, which ultimately, again, is going to be temperature dependent. And so the reaction rates are strongly temperature dependent, but also are somewhat random based on the molecular orientation. I'll talk a little bit about those in a little bit more detail here. So for molecular orientation, again, for the A plus B goes to C plus D simple reaction, if you have A plus B with a reactive site, as I show here, oriented, in this case, both of them oriented facing the same direction, facing each other, when that collision occurs, provided that those reactive sites are oriented properly, they'll form an activated complex, which is sort of an intermediate step in the reaction. And so when those two molecules, or atoms, or whatever they are, come together, they can form this activated complex where the reactive sites are now interacting. And then in the final step, the molecules transform and separate. So once the exchanges happen, maybe it's an ionic reaction where an electron is changing from one place to the other. Once the activated complex separates, the two compounds have transformed now into C and D, the products. And that only occurs if the molecular orientation is correct. If the reactive sites in A and B weren't lined up properly, you wouldn't be able to form the activated complex, and therefore you wouldn't have the transformation or the actual reaction proceeding to C and D. On the other hand, related to the energy of the collision, this is where we get into talking about activation energy. I'm sure you've seen this in your first year chemistry class, but here's a simple diagram looking at the energy on the y-axis and the direction of the reaction, either going forward or reverse on the x-axis. So if you're going forward, starting with reactants A and B and going to reactant or product C and D, there's a certain amount of energy, this energy barrier or activation energy, that must be achieved or must be exceeded in order for the reaction to occur. And that activated complex requires a certain amount of energy to form. So that intermediate step in between A and B and C and D needs a certain amount of energy present. Otherwise, the reaction simply will not proceed. So in this case, in the forward direction, there's a certain activation energy. And then in the reverse direction, it's actually a bigger activation energy. There's a bigger hurdle to climb. And so in this case, you wouldn't have the same reaction rate going forward as you do going reverse because of the activation energy difference between the two directions. So yeah, like I mentioned, they're usually different going forward and reverse, which means there's going to be some sort of preferential direction for the reaction occurring. And that energy ultimately is going to be related to the temperature of the system. So the more energy in the system, the easier it will be to reach that required energy to form the activated complex to then allow the reaction to proceed and to go to the lower energy state. So looking at both the molecular orientation, whether or not the molecules are lined up properly, and the energy of the collision, making sure that they have enough energy to get over that hurdle in the activation energy diagram, ultimately it comes down to a question of probability. So the probability of a reaction is going to depend on a few things, but it's basically like this: 1 out of every billion to 1 out of every million collisions. So for every collision that it's occurring, it's a pretty unlikely occurrence that it's actually going to result in a reaction, but there are so many collisions occurring in a short period of time that ultimately a reaction can proceed just because of the high rate of collision. So yeah, 1 out of every billion or 1 out of every million collisions, that's the range. Now there are some things that you can do to increase the reaction rate, and thinking about what the reaction rate is dependent on will give you a clue as to what you can do. First, you could increase the temperature. So because the collision rate is a function of the temperature, how much the particles are moving around, also the energy associated with those molecules is directly related to the temperature of the system. By increasing the temperature of the system, you will not only increase the rate of collision, but you'll also increase the energy of the collision, which will therefore increase the probability that the reaction will occur. Similarly, if you increase the pressure, now you're not going to affect the energy of the molecules themselves, but you will increase the collision rate, because if you increase the pressure, it means the molecules will be confined into a smaller space. They'll be closer together, which will increase the rate of collision. Now, here's sort of hypothetically, you can ask yourself, what are some of the limitations of operating with both a high temperature and a high pressure? Ultimately, it comes down to a question of material selection. So if you want to have a reactor operating at a really high temperature and a really high pressure, you need some material that can withstand those conditions. Now, metals are usually good for reaction vessels, but even at high temperatures, they have melting points. So like that metal can only withstand a certain temperature and pressure before it starts to break down. And ultimately, that's what's going to limit, in many cases, the operating conditions for a reactor. So you can't just go to an infinitely high pressure or an infinitely high temperature because of the materials that are required to actually enclose or encase the reaction. Now, what are some other things you can do to improve reaction rates or improve the likelihood of reactions to occur? This is where catalysts can come in handy. They allow the reaction to proceed at a much lower temperature and pressure because they reduce the activation energy required for the reaction to occur. So here's a simple diagram showing again the activation energy with and without a catalyst. So without a catalyst, that was the big high peak that we saw previously, but by including a catalyst, the catalyst allows the reaction to occur with a lower energy required. It allows that activated complex to form, partly because it helps orient the molecules and requires less energy for that activated complex to actually form. And therefore, you have a lower peak on this activation energy diagram, and the reaction will occur with a much lower energy and therefore much lower temperature. The way catalysts work, essentially they're porous structures, meaning they have a lot of sort of empty space in amongst the solids. So here's just a diagram of a porous solid particle. You can see these little tubes here, they would be the pores, and those pores provide a high surface area over which the the reactants can interact with each other. So the first step would be a mass transfer step where the reactants would diffuse into the pores. That would be a molecular diffusion based on a concentration difference. The reaction then proceeds sort of within those pores on the high surface area of the catalyst. That reaction would look like this. So first, the reactant A would adsorb to the surface, and adsorption is when an atom or a molecule physically adheres to a solid surface. Now, it does so in a way that leaves the reactive site exposed, and so it would orient itself if the catalyst is selected properly so that that reactive site is ready to interact with reactant B that comes along. That then forms the activated complex, and because the reactive site is exposed, it's easier for that activated complex to form. The two atoms, the products, then dissociate, so they break apart after the activated complex is formed, and then they become unique new products. And then finally, product D, which would have been previously adsorbed to the surface, now desorbs and would then be carried away in the stream into the surrounding reaction vessel. And that would be, again, a mass transfer process. So here you're going to have an interaction between mass transfer and reaction kinetics, but ultimately the point of this is that with a catalyst, the activation energy is lowered because the activated complex can form at a much lower energy due to the orientation of the adsorbed reactant A. Now, we can write some mathematical expressions that describe reaction rates, and generally they're going to take the following form. Just for a simple reversible reaction, it looks like this. So if you have A plus B going to C plus D with stoichiometric coefficients A, B, C, and D for each of them, and this would have to be a balanced reaction. So for a given reaction that you're looking to look at the reaction rate, you would have to first balance the reaction, which I'm sure is something you've done in chemistry. You can then write the reaction rate. And you can do it in terms of any species. Here I've written it in terms of the rate of reaction of species A. And there are two terms. There's first the forward reaction. So this is the consumption of A and B. So what you have is this K constant, Kf, and the subscript F just indicates the forward reaction. So the forward rate constant multiplied by the concentration of A raised to the power of A, which is the stoichiometric coefficient of A, multiplied by the concentration of B raised to the power of little b, that's the stoichiometric coefficient. So that's the forward reaction rate minus the reverse reaction rate. So you would have the reaction rate constant for the reverse reaction, subscript R, concentration of C raised to the power of C, concentration of D raised to the power of D. And essentially what this does is it tells you the rate of reaction or the rate of consumption of A is related to how much A is being consumed in the forward reaction minus how much A is being produced in the reverse reaction, because if you think of the reverse reaction, that would actually produce A, and that would ultimately give you the rate that A is being consumed. The dimensions of this equation, so the reaction rate is in terms of moles per time per volume, or moles per second per meter cubed, and that gives you sort of an idea of how fast the reaction rate is occurring per unit volume of the system. Kf and Kr, like I mentioned before, those are rate constants. Those are specific to a reaction, and those are determined experimentally. And they're for the forward and reverse reactions based on the subscript. So F is forward, R is reverse. A, B, and C, and D are all the stoichiometric coefficients in the balanced reaction. So that's the first step, is you always have to balance your reaction, and then you can figure out the power law dependence or the rate dependence on the total reaction rate. So if you're given concentrations and a reaction which you can balance and some rate constants, you could figure out the rate of that reaction occurring. So right now I'm going to do a quick example just indicating the a solution for a reaction rate problem, and I'll be back shortly. So for this example, I'm going to look at the reaction of species A reacting to form product C. So just with a few pieces of known information, the initial concentration of A is 0.74 molar, or that's 0.74 moles per liter. The reaction rate constant K is 0.015 seconds to the -1. Here all of A is reacting, so it's a complete reaction. A goes to C, and in this case we'd be asked to find what is the rate of consumption of A, so the reaction rate. That's the unknown information here. So we can set it up. The equation, the reaction rate, is based on the reaction rate constant K and the concentration of A. R equals Ka, so we can plug in our K value, plug in our concentration, and we get a final answer of the rate of consumption of A of 0.01125 moles per liter per second, or 0.01125 molar per second. Just doing a quick check, that makes sense. It's a little bit smaller than the rate constant, and the concentration was a little bit below 1, so the value is reasonable. So in this case, all of A is being consumed, and this is useful just on its own to know how fast the reaction is occurring. It can also be useful in determining reactor volume. And we're back. So that wraps up the reaction engineering section of the course, the lecture 1 in section 4. In terms of the overall hydrochloric acid neutralization problem, in this case the reaction that occurs between the sodium hydroxide and hydrochloric acid is so fast that the reaction can occur almost instantaneously in a mixer. So we don't need a big reaction vessel allowing for some long period of time for the reactants to mix. It happens pretty much instantaneously. So as we move forward, we'll look at an updated PFD of the system. It's going to just include a mixer in the reaction scheme because there's no large reactor required for that reaction. So in the next lecture, I'll be discussing heat transfer. So when you have these products that come out of the reactor that are now hot, what do you do with them before discharging them to the environment? So I'll see you there.